All right, today we're tackling one of the most fundamental rules of the universe, a law that's been considered unbreakable for 50 years, given to us by Stephen Hawking himself. But what if the whole reason why this rule exists has been completely misunderstood? What if it's not about the geometry of space at all, but about the very substance of nothingness? So let's kick things off with a question that seems pretty simple on the surface, but has a really profound answer. When a black hole forms, can its surface area, that point of no return, can it ever get smaller? According to classical physics, the answer is a big, emphatic no. It's an ironclad rule. A black hole's surface, its event horizon, can only do one of two things: stay the same size or grow larger. It can never, ever shrink. And look, this isn't just a hunch, it's a full-blown theorem, worked out by the great Stephen Hawking back in 1971. It's called the Black Hole Area Theorem, and for half a century, it has been an absolute cornerstone of modern physics. Okay, so to really get why this new idea is so revolutionary, we first need to understand the standard story. For decades, the only explanation for this unbreakable rule came from one place: Albert Einstein's theory of general relativity. You see, in Einstein's universe, space-time isn't just some empty backdrop for the action. No, it's a real, physical, flexible fabric. And what we call gravity is simply the bending and warping of that fabric by mass and energy. So from this point of view, the area law is a direct result of space-time's geometry. It's basically a rule about the shape of space itself. But what if that's not the whole story? I mean, what if the area law isn't about geometry at all? What if it comes from something totally different? Maybe something even more fundamental than space itself? And this brings us to a fascinating alternative idea: dynamic vacuum field theory, or DVFT for short. Now, this theory suggests something pretty radical: that the empty vacuum of space isn't actually empty. It proposes that space is filled with a real, physical substance, a medium with its own properties, almost like a kind of cosmic fluid. And you gotta understand, this is a huge shift in how we think about things. In Einstein's picture, space-time is the main event, the fundamental thing. But in this new theory, nope, the vacuum is what's truly fundamental. So gravity is no longer the bending of space-time, it's more like a distortion, a ripple, within this vacuum medium itself. Okay, so here's the million-dollar question, right? If gravity is just a distortion of this vacuum stuff, how on earth does it produce the exact same area law that Hawking figured out from space-time geometry? How does that work? Well, in this new picture, a black hole's event horizon isn't just some abstract geometric line. It's a real, physical place where the vacuum medium itself is flowing inward so fast that it creates what's called a trapping surface. Basically, nothing can get out, not even the tiny ripples in the vacuum itself. So this new theory explains the area law with four pretty physical steps. First off, the vacuum medium has what's called positive energy, which gives it a kind of stiffness. Second, this stiffness acts like a lens, naturally focusing any energy or light that passes through it. Third, this means the very light rays that form the event horizon are constantly being focused inward by the vacuum stiffness. And finally, because those rays are always getting squeezed inward, the surface area they create simply can't get smaller. It becomes a physical law, not just a geometric one. So the entire incredibly complex area theorem just boils down to this simple chain of physical cause and effect. The vacuum is stiff. That stiffness stops the horizon from spreading out, which means the area can't decrease. It's that direct. But here's where it gets even cooler. This new way of thinking doesn't just explain the area law. It totally reframes the weird connection between black holes and thermodynamics. And it gives us a new, much more physical gut feeling for why black holes seem to have things like temperature and entropy. So this new perspective basically translates these super abstract ideas from relativity into tangible physical properties. What we used to call surface gravity, in DVFT, that's just how fast the vacuum medium itself is flowing inward. What we call temperature, that's now the actual quantum noise from the trapped waves in that vacuum. And entropy becomes a literal count of all the information that's locked away in the vacuum behind the horizon. This makes these bizarre concepts feel way less like a mathematical metaphor and more like a real, physical thing that's actually happening. The temperature of a black hole is literally the sound of a trapped fizzing medium. The entropy is the information locked inside it. It gives a physical reality to these ideas that were otherwise just, well, abstract. So, wait a minute, we have two completely different theories, right?
They're based on totally different foundations. One is all about geometry, the other is about a physical medium, and yet they both arrive at the exact same conclusion. Why is that so important for physics? What does that tell us?
Well, it's actually incredibly powerful. It suggests that the area theorem is more fundamental than any single theory. I mean, if you can get to the same rule from both geometry and the physics of a vacuum, it hints that the rule itself is telling us something very deep about reality. And this new physical intuition? Well, it could give us a brand new angle for tackling the biggest puzzle in all of physics, the hunt for a theory of quantum gravity.
And this right here, this is really the key takeaway. The unbreakable rule might not be about the geometry of spacetime being fundamental after all. It might be about two even more basic principles of our universe: the idea of a one-way causal trap and the fact that positive energy tends to focus things. Any theory that has those two ingredients, whether it's GR or this new DVFT, is gonna wind up with an area theorem. And that leaves us with a really profound final question to chew on. For about a century now, we've thought of spacetime as the stage on which the universe performs. But maybe spacetime isn't the stage at all. Maybe it's just one of the actors, emerging from some deeper reality that we're only now beginning to understand. Thanks for digging into this with me.